Hi, thanks for tuning into this recording of my Grads 2020 presentation. My name's Gabriel. I'm going to be presenting for you my work on the development of an atomistic model for looking at the fundamental deformation mechanisms in max phases. So here's just a brief overview of what my talk will be. I'm first just going to discuss what max phases are and why we're interested in studying them. I'll also discuss some of the very unique deformation mechanisms present in max phases. I'll move on to the development of our atomistic model and its accuracy in modeling max phases. And finally, I'll discuss a few applications of the model to modeling max phase deformation. So just jumping right into it, an introduction of max phases. Max phases are commonly known as thermodynamically stable nanolaminates, and this is because of their inherently layered crystalline structure. They are ternary carbides and nitrides, where MX blocks, with M being a early transition metal and X being carbon and nitrogen, are interleaved with pure A group element layers. Their layered structure can be formed from a wide variety of compounds, from a wide variety of elements, as seen in the periodic table here. This results in more than 60 plus compounds being synthesized to date. The layered structure of max phases results in a number of unique properties. The presence of the MX layers gives them a lot of the properties which are associated with their corresponding binary carbides and nitrides. This includes high stiffness, good electrical conductivity, and good thermal conductivity. But then the presence of the A layers as well gives them some properties you might more typically associate with metallic materials. These include that they're readily machinable, relatively soft, resistant to thermal shock, and damage tolerant. The combination of these properties together make them a very interesting material to study. So moving on more to max phase, their deformation properties. Max phases are pretty well known to deform primarily by dislocation slip, but the unique thing about this is that these dislocations are only contained within their basal planes, so the direction along which the layers stack. This has been shown in various TEM studies where all the dislocations have been mapped and they fall along the trace of the basal planes. As a result, dislocations can have more limited interactions in max phases. They either align themselves in arrays along the same basal planes, as you can see in an image on the left there, or they can align themselves in walls on adjacent basal planes, forming low-angle grain boundaries or kink boundaries. The presence of only basal dislocations, and hence only basal slip, leads to significant plastic anisotropy in max phases. When basal slip is active, when the basal planes are at an angle to the compression direction, we see deformation by typical slip mechanism, as you would see in metals and other such materials. However, when basal slip is inactive, when the planes are oriented either parallel or perpendicular to the compression direction, deformation occurs by much more complex mechanisms. And just note here in the two stress strain curves, the order of magnitude difference of the stresses. When basal slip is allowed, deformation is much easier than in other cases. Another sort of hypothesis about this mechanical anisotropy is that it results in some of the excellent mechanical damping properties observed in max phases. Max phases are very unique in that they combine excellent mechanical damping with also high stiffness, something that's typically a trade-off in materials. We know that their high stiffness originates from the strong MX bonds, as is the case in typical engineering ceramics, but the mechanisms behind the mechanical damping remain more of a mystery. A number of mechanisms have been put forward, including reversible kinking, microcracking, reverse plastic flow, and elastic buckling. But until now, we really haven't been able to study these mechanisms in detail. And this is where atomistic modeling comes in. Atomistic modeling occurs at the appropriate length and time scales to study these mechanisms that we're interested in. These mechanisms typically happen much too fast to observe experimentally, and they also happen on length scales which are beyond the capabilities of quantum mechanical simulation methods. So this is the simulation method that we are working with. Atomistic models require something called an interatomic potential. This is just a way to describe the forces on all the atoms, and up until now, there haven't been any available interatomic potentials for max phases. We resolved this recently by developing what's called a bond order potential for a titanium aluminum carbide max phase. Here are just a few select properties of the max phase to sort of prove that this potential we've developed is correctly modeling the max phase. And the table there just shows structural properties, lattice constants, formation energy, energy transitions, and all of the values from the bond order potential are relatively close to those from experiment and quantum mechanical calculations. Looking at properties very relevant for the deformation of max phases, the elastic properties. The plot in the bottom left there shows 5 different elastic constants calculated with the bond order potential in very good agreement with density functional calculations. Maybe most important for the description of basal dislocations in max phases is this MA energy surface, which just sort of describes how those layers will slide relative to one another. If we look at the 2 plots below the surface there, which are just simply slices of that contour plot along the 2 axes, we see that the energy results are in very good agreement, again, with density functional theory calculations. So we feel very confident that this model can successfully describe max phase deformation behavior. So the first example I want to show of modeling max phase deformation is nanopillar compression, something that has been able to be done experimentally so we can make direct comparisons. In this case, we have compressed these 3 different nanopillars with the basal planes oriented at 3 different angles to the compression axis, 45, 75, and 90. And we see markedly different stress-strain responses. Similarly to those micropillars I showed earlier, the 90-degree case where we have no basal slip active, the stress is significantly higher than the other 2 where basal slip is active. If we look at snapshots from these simulations, which are color-coded by shear strain, so we can see how the layers have slid relative to one another, we do see the big differences in the mechanisms here. At 45 degrees, we see that the nanopillar is deforming by a classical slip mechanism similar to what we see with metallic nanopillars. Very interestingly, at 75 degrees, the pillar does still slip, but because the dislocations are trapped within the structure due to the high angle, they've arranged themselves into these dislocation arrays like we have seen experimentally in TEM images to form this kinked structure. And then at 90 degrees, when we have no basal slip, the nanopillar ultimately fails by buckling of the layers. The second example I want to show here of modeling max phase deformation is with nanoindentation, something that has been used experimentally to probe the mechanical damping response of max phases. If we look at our simulated nanoindentation force displacement curve here, there's a clear hysteresis loop showing the energy indeed has been dissipated. Now, what we can do differently from experiments is then actually go and look at what's happening directly under the indenter during the experiments to get an idea of what the mechanism is absorbing this energy. And from these images, it does become clear that formation of these kink structures within the layers does play a large role in dissipating a lot of this energy. The kinks form when the indenter goes to its maximum depth, and then they largely dissipate when the indenter is removed. Something that gives a lot of credence to one of the theories of reversible kinking for the mechanical damping observed in max phases. So in summary, the bond order potentials that we've developed now enable new studies of these very unique materials, max phases, and how they deform in these very unique ways. This is the first time an interatomic potential has been developed for max phases, enabling much more studies to be done in this topic. The bond order potential can successfully capture a number of the max phase properties relevant to its deformation, giving us confidence that it is accurately representing these materials. And we can clearly see that the max phase plastic anisotropy leads to a variety of deformation mechanisms, and we can implicate kinking in the excellent mechanical damping properties, as has been previously hypothesized. So I'd just like to, with that, acknowledge some of the funding sources for this project, the Course Tech Fellowship at School of Mines, the Army Research Office, and the National Science Foundation. I'd also like to thank my research group, the Computational Material and Science and Design Research Group, as well as input from Professor Michel Barsoum at Drexel, one of the leaders in max phase studies. So with that, thank you for taking the time to listen to my presentation. I hope you've learned a lot from it.